As electrical engineers, circuits are the first things we learn. We learn how to analyze, design, build, debug, and produce working circuits. However, have you wondered what are the limitations of thinking of electrical systems in terms of circuits? In this video, we look at the foundations of circuit analysis from the perspective of Maxwell's equations and see how this perspective gives us insights. Anytime an electrical engineer or an electronics engineer sees this printed circuit board, the first thing comes to my mind is, what circuit is this? Right? However, you note that the actual printed circuit board is indeed a three-dimensional object, and the voltages and the currents in this board are actually functions of three-dimensional space and time. A circuit, however, is a two-dimensional representation of the same thing. How is it that we can analyze a two-dimensional equivalent and derive useful information about this three-dimensional object? And does this simplification have some limitations? To answer that, we need to look at the foundations of circuit analysis, which is Kirchoff's laws. And we have to look at it from the perspective of Maxwell's equations. So once again, there is an actual electrical system and there is our mental representation of that system in terms of a circuit. The advantage of such a representation is its simplicity, flexibility, and its versatility. However, the limitation is that we are when we have a circuit representation of some system, we are giving up information. We are not using information like how exactly are the components arranged in space, what is the distance between components, and things like that. Now, the question is, when exactly do those things become important enough? And is there a way in which we can modify our circuit representation of those systems so as to retain the simplicity and accuracy? And also we will see under which conditions this representation is no longer useful. So the cost in making a more and more accurate circuit representation may not be worthwhile, and it may be just easier to simply go and analyze your system in terms of electromagnetic fields. So the first law, of course, is the Kirchoff's current law, which states that the algebraic sum of currents in a network of conductors meeting at a point or a node is zero. And in this particular example, you can see that I3 plus I2 is equal to I4 plus I1. However, in the actual physical system that this circuit is representing, this node might be a volume in space. It could be a solder ball, for instance, and it's enclosed by the surface S. So what we will do is we will look at how the electromagnetic fields behave in such a volume surface. We start with del cross H is J plus dou D by dou T. In the second step, we apply divergence for all terms in this equation on the left and right hand side. Now, using the fact that the divergence of curl is zero, this tells us and this gives us the continuity equation, which is actually a restatement of the law of conservation of electric charges. For this to be more useful, we go over from the differential representation to an integral representation. How we do that is we will integrate this expression number 4. We'll perform a volume integration of this expression over the volume of the node. And by using the divergence theorem, the first term, this term, is expressed instead as a surface integral Now you will recognize that the first term, the surface integral of J, is nothing but the sum of directed currents. And the second term is basically the time rate of change of the enclosed charge. If the enclosed charge in the volume of the node is 0, if it's indeed 0, then we can clearly see that the sum of the currents is 0. Next law is, of course, the Kirchoff's voltage law. And Kirchoff's voltage law is basically telling us that the sum of directed voltages across around any loop, of course, is 0. That means sigma of voltages is 0. Now, quickly, this comes, of course, from the Maxwell Faraday law, which is del cross E is minus dou B by dou T. Changing from this general form to a time harmonic form gives us this in terms of the phasor fields with the e to the power j omega t time dependence. In integral form, we will now integrate, perform a surface integral of this equation 2 across the surface enclosed by the loop C. So that is this surface. Now in general, inside this loop, there is magnetic field, and that magnetic field need not be constant over the surface. It is given by several things. One of the things being any externally imposed time varying fields, and secondly, fields generated by current flowing through the components, or maybe fields generated by current flowing in components in some other loop, some other part of this circuit or PCB, for instance, or another PCB altogether, right? So there are many possibilities in which magnetic fields are influenced. And we can now use Stokes' theorem to see that the left-hand side is expressed as the line integral of E, and which we identify as the sum of directed potential differences. Now we clearly see that this equation, the sum of directed voltages, is not 0 under all conditions. Specifically, the presence of magnetic fields within the surface enclosed by the loop is what is causing the sum of voltages not to be 0. So in other words, if you still want to use the Kirchoff's voltage law, you need to have a mechanism by which we will properly account for this term. Before proceeding into that, let us first express this term in a slightly different form. So we know that the divergence of B is 0. So B can be expressed as the curl of A, where A is the vector potential. Now, substituting this, we can express the sum of directed potential differences is proportional to LC upon lambda multiplied by some average value of this vector potential, average on that particular loop. Here LC is the loop circumference. Now we see that if you arrange your loop in such a way that the circumference of the loop is much smaller compared to the wavelength, then this particular term may be much smaller than all the individual terms that make up this sum. In that case, you could ignore this term and still analyze your circuit. Remember that to really evaluate this sum, we need the exact spatial distribution of the magnetic field and the physical layout of this loop as well. We need all that information, which is really not contained in the circuit. So we can get away not evaluating this term under the condition that LC by lambda is sufficiently small compared to the terms that make up this sum. It is also seen that when the driving frequency is 0, then immediately this term becomes 0. So clearly at DC, we don't need to worry about this. So we don't need to worry about at DC and LC by lambda when it is far, far less than 1. However, it is still not clear how exactly small must the circumference be compared to lambda, right? Because we have the second term here, A, depends on the magnetic field. To understand this a little bit further, let us go back to our original representation, this particular term here, and let us now express the magnetic field B and break it down into what are the possible sources for that magnetic field. The first source for that magnetic field is an externally imposed magnetic field. This could be an electromagnet that is moving, or a permanent magnet that is moving, some electromagnetic wave that's hitting your circuit. Any possibility is there for that. And in order to account for this, specifically in machines and so on, we need to calculate something called as the EMF. So if you calculate the EMF properly, you have accounted for this term. Now, in order to calculate this EMF, you really need to know the physical dimension of the loop, how exactly is the loop is in terms of, and what is the distribution of the magnetic field, external magnetic field, and so on. So that information is absolutely essential in order to really get a proper estimate of the EMF. But that's not enough, right? In addition to the externally imposed magnetic field, the components in the circuit, when you drive current through them, also generate their own magnetic field. And the magnetic field generated by the components also is, if you want to really get the exact distribution, it really depends on how the individual components in the circuit are aligned with respect to each other, and so on and so forth. We can, however, make this problem a little bit simpler by breaking the field as the field generated by a component by itself and the field generated by some other component around it. So the field generated by a component by itself, so we assume in this component in isolation, drive it, see what kind of field it generates around itself. Using that information, we can account for this particular term. And we already do this, you already do this by considering assigning an inductance to a component. When we assign an inductance, that's clearly the self-inductance. So we can account for fields generated by the component. This is indeed still remains an approximation, right? Because depending on how the other components are arranged, the field generated by your component also may change. However, this is better than not accounting for it at all. And in AC analysis, in power systems and so on, this assigning an inductance and analyzing the circuit works out really well. The last component, which is very tricky, sometimes tricky actually, to account for, is the fields generated near my component from other components. And this can be accounted for in some situations by defining a mutual inductance. However, notice that to properly assign a mutual inductance, I really need to know how exactly the components are aligned, what is the distance, and so on. So this is the term that is not trivial to account for. And at some point, however, it will become very difficult to account for all interactions between components. And that is the point where you might have to resort to a full field analysis.